Hello, everyone. So this week we kind of have a short lesson. We're going to introduce the concept of energy, really just define it, and spend our time working on the concepts of work and power and how they're related to each other. So because we're going to be talking about work and we're going to be talking about power, right? Those are all things that require energy. So energy then is the ability to do work, right? Just like if you have a good breakfast this morning, you'll be able to do lots of work this afternoon and have the ability to perform all tasks you need to do today, whether it's work or school or things around the house. Well, the same is really with any concept of work in physics, right? You need energy first. Now, again, we're not going to talk about the types of energy yet. We will cover that after the midterm, which will be coming up soon. I'll make an announcement about that. But just, again, know that in order to do work, you need the energy. And again, we're working our way backwards. So energy is the ability to do work. So let's go ahead and talk about work. So by definition, work is a force applied to an object that causes its motion, right? That causes its displacement. A force applied to an object causing its displacement. So as the definition states, then you must have both the force, right? But also you must have a displacement. Otherwise, there is no work. One of each by themselves, it does not qualify work. So again, in order for a force to qualify as having done work on an object, there must be a displacement of the object that's caused by the force. And the reason for why this statement's here is because, as you remember, there are balanced forces and unbalanced forces, right? You remember we talked about the two groups of people playing tug of war. One of the groups, or one of the two groups playing, were of equal and opposite force, and so they are both pushing against or pulling against each other, but the rope does not move. So even though these guys are sweating and getting tired, they would not be doing work because there's no movement. The group that has unequal forces, right, and is that rope is eventually going to be moving in one direction, that's the group that would be doing work according to this definition. And we'll see why that is mathematically when I introduce the formula. So let's talk about, again, mathematically, right? So the symbol for work, it's simple, it's W, right? So easy to memorize, W for work. And the formula is actually simple too. The work equals the force applied times the distance, right? Or the displacement, which makes sense, right? We just said it's the force and the distance that's caused by the force. So you just multiply those two variables and you get the amount of work being done. And now the units are interesting. The units actually have a name for themselves. They're called joules. And what a joule is a newton, right? Coming from the force variable, right? So we have newtons multiplied times meters, which again is the universal measurement or unit of distance, right? So joule is a newton times meters, right? And obviously you can break down newtons. We know newtons are kilograms times meters per second squared. And because the meters in meters per second squared is in the numerator, it doesn't, they don't cancel out, right? You have meters in the numerator and meters on the top of it here, so they both stay. So again, it's newtons times meters, also called the joule. And again, that's also important for you guys to know and memorize. So if we look at this equation, right, they're both variables that are multiplied. So the amount of work, right, the answer, is going to be proportional to either of these two variables, right? It's going to be proportional to force and proportional to distance, right? If you increase the force, you increase the work. But also if you increase the distance, even if the force stays the same, we know you're going to do more work, right? So again, think of if you're a bricklayer, right? If you're building a home and you lift a brick 6 feet from the floor, right? And somebody else is putting bricks only 3 feet high, then you would be doing twice the amount of work, right? Because the distance is double. So again, you were to plug in this number, whatever the force is, since even if they're equal bricks and they require the exact same amount of force to push or lift, because your distance is greater, your work is greater. And the same is true even if the height is the same, right? Let's say you lift that weight or that brick, but one of the bricks is twice as big, therefore requiring more force. Remember, force is equal to the mass times the acceleration. So if the mass increases, your force is going to increase, right? So if you lift a brick that's twice as heavy, requiring twice as much force, you will be doing double the work, right? Even if two people are lifting the bricks at the same height, the person lifting the heavier brick is doing more work, right? And that just makes sense. So again, since work is the force times the displacement, what happens if you apply a force, even if it's a great force, to an object without moving it? So again, imagine you're the guy that's laying bricks, but instead of actually lifting them, you're just holding them above your head, or you're just holding them in front of you. Right after a while, you would be really tired, because again, let's say this is a 100 Newton brick, right, requiring 100 newtons of force to hold up. Are you actually doing work? If you were tasked to build a house, would your boss be really happy when he pays you? Well, let's look at it. You have a 100 newtons of force, but you're doing 0 displacement of the brick. So even if this was a billion newtons, even if it was a billion Newton brick, if you multiply times 0, if your displacement is 0, then what's your answer going to be? Well, it's going to be 0. You've done 0 amount of work. So again, it goes back to that statement. In order for a force to qualify as having done work on an object, there must be a displacement of the object, right, caused by the force. So it's not so much the force, but also the displacement. All right, so let's do an example. All right, and I think the examples, it's just hard to make them hard, or hard to make them difficult, right? It's difficult to make them difficult because the formula is simple, I think. The concept, I think, is simple. So imagine you're stranded, right? You run out of gas on the street, and you see a gas station 2 meters away, right? How much work would be performed if you had to use 5,000 newtons of force to push a car forward a distance of 2 meters? All right, now again, we are going to do very simple math for these equations. Work itself is a vector quantity, right? You could talk about forward force, you could lift something, you can push something against gravity, against friction, against air resistance, and you would have to plug in all those variables. But for us, it's going to be very simple. It's simply going to be the force times the distance. We're not going to worry about any of the other sort of invisible forces, right? For our purposes, we are pushing a car in outer space where there's 0 resistance from the push. So if we are giving the force, right, 5,000 newtons, and we're giving the distance, it should be very simple for you to multiply 5,000 newtons times 2 meters, right? That's simply 10,000 newtons times meters, or 10,000 joules. So it requires 10,000 joules of work to push a car that requires 5,000 newtons of force to a distance of 2 meters, right? So I think that's very simple. Now, sometimes you're not given force, right? So force is something that we should still be able to calculate. So here's an example of that. A soccer player kicks a ball that weighs 10 kilograms. So again, we know its mass at a rate of 10 meters per second square. So if we're giving something that's in meters per second square, we know that it's its acceleration. Okay, so we know the weight, we know the acceleration. The soccer ball then, after you kick it with that much force, moves a distance of 52 meters. How much work did the soccer player do by kicking this ball? So again, first we need to figure out how much force was applied, and thankfully we are giving just enough information to do that, right? We know that force is equal to the mass times the acceleration. Again, you guys all should know this, should have this memorized and engraved in your head. And the mass, since we measure it in kilograms, is 10 kilograms times the acceleration of 10 meters per second squared. That's an easy mathematical, right, calculation. That's 100 newtons. So we have 100 newtons of force. So now that we know the force, we can then plug it into our equation, right? So we're going to plug in the 100 newtons, and we know the distance is 52 meters. So our work is 5,200 newtons times meters, or 5,200 joules. Okay? So again, really for a class, you may just, you could just change the numbers and figure it out, right? It's not that hard to think of other examples. It's, like I said, we're not going to make it any more difficult than this. I know if you watch the Khan Academy examples, they go on very complex mathematical equations, because again, there's all these other forces, right? There's vector forces, there's angle theta, there's friction, there's air resistance, there's gravity. These are all things that in reality we need to compute and calculate in our formulas. However, again, for the scope of this class, we're not going to do that, right? We're not launching a rocket ship into outer space, so it's okay that we just get close to the answer, right? So again, we're just kicking the ball in outer space. So hopefully that makes sense to you, right? The concept of work. And the next sort of obvious subject then is to talk about power, right? Because not everybody can do the exact same amount of work, right? Some people are just more powerful than others, right? It could do more work. So then the definition of power is the rate at which work is done. Simply put, is the time that it takes to do the work. So then power then is letting us look at the time required to perform the work, right? We can then see how fast we can do the work. All right, so the definition of power is the rate of doing work. The symbol, again, is very simple and easy to remember. It's P for power, right? And then the units also have a name of their own. They're called watts, right? So think of your light bulbs at home, right? We can tell how powerful a light bulb is by looking at how much wattage it gives out. And a watt for power is just equal to a joule divided by a second, right? So 1 watt is 1 joule per second. And again, if we look at the units, you could almost see the equation, right? So we know that for power, we need to divide the work done and then divide it by the time it took, right? So work in joules divided by the seconds it took to do this work. So I think also very simple. So now, because there's, these two variables are not on the same numerator line, right? One's a numerator, one's a denominator. We know that if you increase the work, you're going to increase the power. But if you increase the time it takes to do the work, then you're actually using less power or producing less power, right? So again, time is going to be inversely related to power, where work is going to be directly related to power, right? This goes up, the power goes up. If time goes up, then the answer is decreased, right? Power is decreased. So again, let's look at the person that was stranded before, right? From the previous example. So we know that he pushed the car, right, 2 meters in a time of 30 seconds. So now we're given the time. How much power is exerted? So again, we know the work, and if you don't remember, we got an answer of 10,000 joules, right? The force applied times the distance. And if power is work divided by time, then we just simply plug in our work, which is 10,000 joules, and divide it by the 30 seconds it took. And again, if you plug this in a calculator, you'll get 333.3333, right? We could just round up or round down to 333, make it a whole number. And so that's our answer, 333 joules per second, or 333 watts. Okay, so again, it's as simple as that. We need to be able to formulate for work, and then we divide it by the time in seconds. So now, let's talk about this concept, or let's think about what this means, right? If you have two engines that do the same amount of work, why use the more powerful engine, right? Let's say you have two cars available to you to drive to school today or to work, and one's a Prius, and the other one is a Ferrari, right? Why drive the Ferrari other than that it looks cooler, right? So the reason is that the more power available, right, means that it takes less time to do the work, right? As we saw, the time is inversely related to the power. So the less time it takes to do the work, the more power you have, right? The more powerful engine can get you there sooner, right? Now, power itself doesn't really affect work. It's the opposite, right? The same amount of work is required to lift a transducer to a given height, no matter if it takes 1 second or 1 hour, right? So the work itself is the same, but power there really looks at how long it took you to do that work. Okay. And just to recap again, we talked about work and we talked about power. Make sure you know their definition, right? Make sure you know their formulas, and make sure you know their units, right? And understand how each one of these variables will then affect the answer, right? Since these two are multiplied, they're both directly related, and this, since time is indirectly related because it's divided by it, right? We're dividing the work by the time, and so the more time it takes, the less power, and vice versa. Okay. All right. If you have any questions, again, you can post a question in the boards or send me a message directly. Okay. Have a good week.